Hello, welcome to part 6, acid-base equilibria. In this one I'm going to cover strong acids and bases and do some calculations with that. Now, pretty simple, the idea of strong acids and bases. For example, let's say we have some nitric acid. Okay, let's say that I've got 0.2 molar. I put 2 molar solution. It's a liter of nitric acid. What is going to be the concentration of hydroxide ions, hydrogen ions? Well, that's going to completely dissociate, so it's going to be 0.2. So that's pretty simple. Like, what you put in is what you get out, because it's got complete dissociation, and we know that they're strong because our resulting ion here is neutral, meaning it doesn't contribute at all to pulling this back out or pushing it back the other direction. So strong acid-base calculations in that sense are really simple. Put it in, and then how would I figure out the pH of that? Well, the pH is simple to figure out. Let's use a different color right here. So pH, we've talked about it before. pH equals the negative log of the hydrogen ion concentration. So strong acid is really simple. If you know the concentration you put in, that's the concentration you get out. On the other side, you can take the negative log of that and quickly find the pH. We also have this concept of pOH. So pOH is just simply the negative log of the hydroxide ion concentration. Not used quite as often in everyday language, but in chemistry, certainly it's used. Now, what about if I had a pH and I wanted to figure out a concentration from that? Well, the concentration of my hydrogen ions is going to equal the antilog. Let's see, that's not antilog. Here we go. We'll just do it like this. The antilog of the negative pH, or vice versa. The hydroxide ion concentration is going to be the antilog of the negative pOH. And then similarly, pH then plus pOH equals 14. So when you add these two together, it equals 14. So if you solve for a pOH and you want to find the pH, you just subtract it from 14, vice versa. So that's pretty simple. And then also, like in the last video, we showed you the concentration of the hydroxide ions times the concentration of the hydrogen ions always equals 1.0 times 10 to the negative 14th. So that makes it simple to actually solve for concentrations that way. Or you could take the antilog. So as far as pH calculations go, this sort of gives you everything that you'll ever need in that respect. So let's look at a couple of quick little examples here, and then we'll move on. Doing something like this is quite simple, because all you got to do is whatever you put in, what you get out, take the negative log of that. But let's say that we did something a little bit more complicated. Like, for example, let's say that I mixed 2 acids. Let's say that I had HCl, and I'm going to mix that with hydriodic acid. So I have hydrochloric acid and hydriodic acid. Let's say that these are different molarities. Let's say I have a 0.022 molar hydrochloric acid, and let's say that I have a 0.015 molar hydriodic acid. And just for fun, let's say that I have 21 milliliters of this and 30 milliliters of this. All right, so what's going to happen as far as what's my pH? So here's the question. What's my resulting pH if I mix these two things together? Well, you know that each one's going to completely dissociate. And from the information here, you can find out exactly how many moles that you'll have. And then you'll also know the total volume that you'll have, so you'll be able to find the resulting concentration. So real easy to do. If I have a 0.022 molar situation, I'm talking about that's in 1 liter. Well, I don't have quite 1 liter. I have 21 milliliters, so 0.021 liters. So if I cross multiply that, I'll figure out the moles of that. So these are put together, so I'll have to add that to the moles of this. So to solve for the moles of this, it's going to be 0.015 molar, and that's going to be over 1 liter. And so I want to know exactly how many moles I have only in 30 milliliters of that. So I don't have a full liter. I have a 0.030 of a liter. So if I cross multiply and divide there, I'm going to get that answer. I just quickly did that in my calculator, and I found that that if I add these two amounts of moles together, I end up with a total of 9.19 times 10 to the negative fourth moles. Well, so there you go. So now I know my total number of moles of hydrogen ions, because that's my total number of moles of both of these put in, taking a little bit of this and a little bit of that. Now, I need to know my total resulting volume. When I add these two together, it increases the volume of both of them. So I have a 0.051 liter solution at this point when I've put in these two together. So if I divide that by that, I get a resulting concentration of, oopsie, I got that off a tenth, so of 0.018 molar. So 0.018 molar, to find the pH, do like we talked about earlier, take the negative log of that. So the negative log of 0.018 equals 1.75. So 1.75 is my resulting pH if I added these two together. So a little bit more complicated, but still quite simple, because you know that all of this is going to become hydrogen ions and all of that. So let's look at bases. Bases, the same kind of situation. What if I was to ask you what the resulting pH is of potassium hydroxide? And let's say that I had a 0.025 molar solution of potassium hydroxide. Well, here's what's going to happen. It's going to make 0.025 molar hydroxide ions. So I know my concentration of hydroxide ions. So what I can figure out is my pOH. So my pOH I know is going to equal the negative log of my hydroxide ion concentration, which in this case is 0.025. So what does that equal? So if I take 0.025, my pOH is going to be 1.6. So the pOH equals 1.60. So that's not pH, but it's pretty simple to find pH, because pH plus pOH equals 14. So then all we got to do is 14 minus 1.6, and my pH then is going to equal 12.4. And that makes sense because it's a base. It's going to have a very high pH, going to have a low pOH. Now, what about this one? In the case of dibasic bases like this, barium hydroxide, and you have a couple other ones. There's two other dibasics. In very low concentrations, they do oftentimes completely dissociate all of these hydroxides. And so for the sake of calculating strong bases, it's safest to expect that you're actually going to get 2 moles for every 1 mole of this. So then what would be the resulting pH then if we had also a 0.025 molar solution of barium hydroxide, being that it's dibasic? If this is dibasic, if we have 0.25 molar of this whole thing, and each one of them gives off 2 hydroxides, well, then we're looking at 0.050 on our concentration of hydroxide ions there. So if we take the negative log of that, the negative log of our 0.050 molar, we're going to get 1.30. And if we take and we subtract that from 14, we're going to get a pH of 12.70 is our resulting pH of that solution. Now remember, keep in mind, if you're solving for hydroxide ion concentrations, the negative log of that gives you a pOH, not a pH. And so if they ask you for pOH, POH, that's it. That's your answer. But if they ask you for pH, you do have to subtract it from 14. So I hope this helps on solving strong, weak acid base problems.